Okay, let's look at positive and null recurrence for the renewal chain. We can begin with the definitions. Right, so recall that that a state is positive recurrent if the expected return time is finite. This is a significant strengthening of the recurrency condition, rho x is equal to 1. Right, that one just says you have a finite return time with probability 1, but this positive recurrence condition adds on the fact that the expected value must also be finite. So that's a much stronger condition. Of course, you've seen that here you have an example of this is an updated version of the note where I have the correct definition of a random variable that's finite. It's finite for every single outcome, but its expectation is in fact infinite. So this should show you that you can have a recurrent state that's not positive recurrent. And then on the other hand, for any random variable with a finite expectation, you must have that the probability that it takes on the value infinity must be 0. That's just expanding out the definition of the expectation. You see that immediately. What does that also tell you? It tells you that the probability that y is less than infinity, which is the complement of this set, must be equal to 1. Okay, so all of this is related to these recurrence definitions, and also should help explain why I say here that note that when a state is positive recurrent, it is also recurrent, but not the other way around. A recurrent state doesn't give you positive recurrency, but a positive recurrent state will give you recurrency. Note that I also put I should explain why I put recurrent here in parentheses. Once you conclude that that expectation is finite, you automatically have a positive recurrent state. Whereas if you want to show that something is null recurrent, meaning that the expected value of the return time is infinite, you must start off with the recurrent state. So read through that and hopefully this all makes sense. And here let's try to work through the example. So for one, based on the comments that we just made, we're going to have to assume this condition. This condition is the one that guarantees us recurrency of the renewal chain, also its irreducibility. And if I don't assume that the chain is recurrent, there's no hope of it being positive recurrent. Right? That's just the same as saying that if I have a random variable that takes on the value infinity with a positive probability, I'm not going to get a finite expectation. And at the same time, we also remember this condition gave us irreducibility, and so again by theorem 1, once you have irreducibility, all the states fall into one bucket of these three. They're either going to be all transient, all positive recurrent, or all null recurrent, and that allows us to just show or exhibit the one of those properties for any one of those states and then conclude it for all the states. And so I'm going to work with the state 0 again. Right? This is the hitting time of 0, the first time the chain hits or enters state 0. This variable gains the interpretation of a return time as soon as I assume that the initial condition is the same, namely 0. And so the subscript here indicates that we start at 0 and look at the expected value of the hitting time, which because of the 0 starting point has the interpretation of a return time. So the expected return time is what we are looking to compute. That should be easy to do. We've already seen the distribution of the number of steps that it takes to return to 0. Once you have the distribution, you just plug in a simple calculation for the expected value, the value that it takes times the probability with which that happens. And so now, here we have it. If this series converges, and of course this prerequisite condition for recurrence holds, then you have a positive recurrent renewal chain. If we want to argue for null recurrence, again, we must assume recurrence. If you want to tack on the word null, you have to start with a recurrent chain. Once you have recurrency and also the same condition for irreducibility, again by theorem 2.1, right? Again, this one, top one, we must exhibit that this expectation is infinite, and as soon as we do that, we have concluded null recurrency for every state. And so that this just means that this series diverges. So the condition for null recurrency is qx is greater than 0 for all states, and this series is equal to infinity. So that's the breakdown of these two. And you can kind of ponder as to what null recurrence really means, right? What does it mean to return in a finite number of steps with probability 1 and yet have that expected value be infinite? The expected return time is infinite, but you still return in a finite time with probability 1. And so that's the kind of the curious nature of math and random variables, and the way, you know, sums converge or diverge, but it is what it is, and these definitions are just motivated by these mathematical properties.